Hello, fellow students. Today, we are going to talk about the Greek letters. They are used very extensively in maths and physics, so I thought it would be a good idea for you to familiarize yourself with these letters so that you won't be intimidated by your teacher if your physics teacher just writes some very strange and cool-looking symbols on the blackboard. It's called ta Ellenica grammata. So the first one is alpha. It's just the same as the English A, and it's where the name alphabet comes from because it's the first letter in the Greek alphabets. And the uppercase use is mainly for the magnetic vector potential. So the magnetic field B can be found out by the curl of A. For those of you who aren't familiar with vector calculus, the curl is just an operator that takes in a vector function and takes a bunch of partial derivatives to it and then give you another vector. For the lowercase alpha, it's used to represent the alpha particle, which as scientists later found out is just a helium nucleus without two electrons. And the word helium is also from ancient Greek helios, which means the sun, because there's a lot of helium in the sun as a result of the fusion of hydrogens. And next letter is beta. This is used to represent the magnetic field. It's also called the magnetic flux density, but don't ask me why it's a letter B, not M. And as you know, the magnetic field can make a Mancker's term and can also exert a force on moving charges, which is the Lorentz force. And the lowercase beta, this is used to represent the beta particle, which later discovered to be the free electron. And the word electron is also from ancient Greek electron. This means amber, because ancient Greeks discovered that if you rub fur with amber, then it will become negative charged, which means a lot of electrons had transferred to it, and hence it's given the name. Okay, now the third letter, gamma. Sorry, it's AB gamma, it's not ABC. There's no C in Greek. And now we enter the realm of relativity. The uppercase gamma is used to represent the Christoffel symbol. As you can see, it's a very oval expression. That's why it's sometimes called the Christoffel symbol. It is composed of the metric tensor G, and I think it's why it got its representation of gamma, and also the derivatives of the metric tensor. And these two formulas are basically equivalent to the first one. Is just a shorter and easier way to write it, because you know there's a lot of derivatives here and physicists are too lazy. They didn't bother to write all these derivatives. So this partial x of the beta index, that's the beta coordinate, can be simplified to just a partial beta and followed by the function you are taking derivatives on. As you can see, it is a lot easier because you don't need to write a fraction. You can just write a symbol in front. And if you want to be even more lazier, you can just put a comma after the function you are taking the derivatives and then put the corresponding index of which coordinate you are taking. So the Christoffel symbols are essential things used to calculate the geodesics in a curved spacetime. And for the lowercase gamma, it's used to represent the Lorentz vector. This here is the ratio of your measured speed with the speed of light. And it tells you how much time is dilated and how much length is contracted for a moving object. The fourth letter is delta. The uppercase one represents the change in the quantity. So delta x means your final x minus your initial x. You may have seen this in your elementary physics class, where the speed is the changing x, delta x, divided by time. And the lowercase delta is used to represent the variation in the quantity. So the variation of y of x, a function, is the y bar, the slightly varied function, minus the original function. And it can be represented abstractly as this. This is your original function, and you vary it by a little bit to get a varied function. And you need to keep the endpoints fixed. This is mainly used in calculus of variations, where we will set this variation to 0. That basically means the function can't be changed anymore. It's at its best, its optimum value. The fifth letter is the epsilon, and it's the same as English E. it used to represent the electric field, a very subjective name, E. And the electric field tells you the electric force acting per unit charge in the field. And because the field is also a vector quantity, it tells you the direction a positive charge will move if placed in the field. The lowercase epsilon can be used to represent the vacuum permittivity, or just any permittivity in general for any material. The vacuum permittivity will have a 0 as a subscript. So in Coulomb's law for vacuum, you have this form, where the vacuum permittivity acts as a scale factor to tell you the relative strength of electric force. It's very large compared to gravitativity. It's 10 to the power of negative 12, but because it's in the denominator, you make this force very large. The next letter is zeta. So it's only our start in Greek alphabet, but now we are at our last English letters. So the uppercase zeta is the atomic number of an atom. So for any atoms with symbol X, the upper number A is the mass number, and the lower number Z is the atomic number. This tells you how much protons are there in this atom. And for the lowercase zeta, it's used to represent the Riemann zeta function. So it's basically a summation. If you put z equals 1 here, you get 101 plus 102 plus 103. So basically the reciprocal of all the natural numbers and then sum them together. And this at the first only works for positive integer z, so 1, 2, 3, 4. And only for 2, 3, 4, this infinite series will converge. For 1, it will not converge. It will blow up to infinity. But analytic continuation leads to complex value of z can also be inserted into this function. And this function is the basis for the famous Riemann hypothesis, which basically says this number z, if you put anything with a real part of a half and some imaginary part, will make this function 0. Actually, it's not this function, it's another function. It's a continued function. But this is the original function. It's later get expanded into a longer form. And the next letter is eta or eta. It's written like an H or an N, but actually it's a vowel. So its uppercase is used to represent the Hamiltonian operator. It represents the total energy of a quantum system. It's just defined as the sum of kinetic and potential energy. The first one you may represent as the kinetic energy operator, because one form of kinetic energy is just your momentum squared divided by twice of your mass. And this is the potential energy. For the lowercase eta, it's used to represent the efficiency of a heat engine. And in the current engine, the efficiency is given by 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. The current engine is the best heat engine you could have. It has the maximum efficiency, which only depends on the temperatures and not on other factors like friction. And next one is theta. Both cases are used to represent angles, but the lowercase is used more often. You can use the uppercase if you have many angles to label, and the lowercase has already been used. And as another word, you need to remember your tricks. So if you have a right angle triangle, the sine of theta is opposite over hypotenuse, and the cosine is adjacent over hypotenuse. This is very important for physics, especially in classical mechanics. You need to make sure you know all of them. The next one is iota. The uppercase is used to represent the conventional current, defined as number of charges passing through a point per unit time. And although the current is a scalar quantity, it has a direction, and you need to remember its direction is in the flow of positive charges. Although the charge carriers in most cables are electrons, which has a negative charge, but because in the early days people don't know there's a thing called electron, so they just define it as the direction of the positive charge flow. And the lowercase iota, it looks like I, sounds like I, but it's not I, because it's missing a dot at the top. And it's not used in any scientific context I can think of. It's really used. But you can just use it for fun if you have something like I. The next letter is kappa. The uppercase is used to represent the cow. It's a family of 4 mesons with these quark compositions. They are mesons, so they will have one matter quark and one antimatter quark in them. So for example, the kaon with a positive charge is composed of a up quark and an anti-strange quark. These particles are very strange things because they violated the charge parity symmetry, which is actually a very important thing, and the physicists think it's true before. But after the kaon, physicists have to invent the charge parity time symmetry. Physicists love symmetries, but they will get very frustrated if they found a symmetry is broken. They might even invent new theories to preserve the symmetry. And the lowercase kappa is used to represent the curvature, and I guess it's where its name comes from because it's a curved sound. It's defined as 1 over r, where r is the radius of the spherical tangent to the curve. So if you want to calculate the curvature of a curve, so for example at this point, what you intuitively do is you draw a circle at this point where its edge is just touching the curve, and then you measure the radius of this circle, you take its reciprocal, then you get a curvature. But however, there's various formulae for curvatures out there, because you may guess this formula is not very practical because it's hard to draw a tangent circle to a curve. You may not get the exact answer. To get the exact curvature, you have to use some other formulas, and these formulas are very complicated to use. And the uppercase lambda is our next symbol. It looks at A with the middle stroke missing. It's used to represent the cosmological constant. Einstein initially added to his field equation to prevent the whole universe from collapsing, because everything in the universe exert gravity on each other, and they'll all be attracting each other. If you assume a universe is not infinitely big, there has to be something that pushed all the things out to prevent them from all crunch together. But he later removed it and thought it was his biggest blunder. So he thought this thing is actually not correct and removed it from Einstein field equations. However, today, lambda is used to account for the effect of dark energy on the expanding universe. Because modern cosmologists actually hypothesized a thing called dark energy, they will make the universe expand and even accelerated its rate of expansion, so they have to add this factor in. But it's a very small factor, as you can see the extremely small number here. So the effect of expanding universe is not very great. And the lowercase lambda is used to represent the wavelength. For a classical wave, it's the wave speed divided by the frequency. But for matter wave, it's the Planck constant divided by the momentum. So it basically applies to anything, even you have a wavelength. Next letter is mu, it's just the m, and the uppercase is used to represent a big mass. So in Newton's law of gravitation, the gravitational force is given by the gravitational constant times the product of two masses divided by the square of their distance of separation, where the big M will typically represent the big mass. So it will be the bigger mass of the two, such as the mass of the sun, the mass of the earth. And the lowercase mu is the reduced mass. This is a very useful quantity used in astrophysics to reduce a two-body problem into a one-body problem. So for example, for the Earth and the Sun system, even though the Sun is moving, because the Earth also exerts a gravitational force on it, we could effectively treat the Sun as stationary if we use the reduced mass for the mass of the Earth. So that means we can just put the Sun in the center of our coordinate system and assume it's not moving, and instead we use the reduced mass for the mass of the Earth. That means we multiply the mass of the Sun and the mass of the Earth together and divide it by the sum of their mass. However, in this case, because the mass of Earth is much smaller than the mass of Sun, its reduced mass will approximately be just equal to the mass of Earth. Next letter is nu. Uppercase is same as the English N. It's used to represent the normal force. And if you're sitting stationary, M equals mg. It basically says that the normal upward force provided by the chair is equal to the downward weight of yourself. This must be the case, otherwise you will sink down. And for the lowercase, nu is used to represent the frequency, especially for the energy of a photon, where it's given by the Planck constant times the frequency of the photon. And just a reminder, F is also used to represent the frequency, but it's typically for a mechanical wave. So it's water waves or string waves. and the nu is typically for electromagnetic waves. The next one is psi, and for the uppercase, I have never seen it used in any scientific context, but it's a cool looking letter. You can use it for some places if you like. It's very cool and astounding to write Greek letters. But for the small lowercase one, it's used to represent the x-coordinate of the critical point in the mean value theorem. So what this theorem states is that basically if f of x is a continuous function in the interval a and b, and is also differentiable in the open interval a and b, then there's a point psi in a and b such that the derivative of f evaluated at psi will be equal to fb minus fa divided by b. This basically states that the slope of a tangent in the interval will be equal to the slope of the secant. So you can see the derivative is dy by dx, which is the slope of a tangent, and it says that these things has to be equal. There's a parallel line. You can think of yourself, why is the case? It must be true if this function is continuous. The slope of tangent must at somewhere equal the slope of a secant. Otherwise, it can't reach this point. The next letter is Omicron. It's the same as English O, and the uppercase is the big O notation. This is used to give the order of magnitude of an approximative function. So for example, when x approaches to 0, if you tightly expand your sine of x out, you will get this. And this is a very important Taylor expansion formula. Please remember this. And if your x is very small, this term is obviously very small, because if you enter your calculator like 0.001 and to the power of 5, the number is very small compared to these first two terms. So you can just omit these terms and just write down O of x to the power of 5 instead. This means there are some more insignificant terms of order 5 or higher after these two terms. These two terms are the important ones. The rest of them terms are not important. And for the lowercase, it's similar. For the small o notation, it's a bit stricter than the big O. And using the same example, again, sine of x near x equals 0. If you are really near 0, or if you're just an engineer, you can even omit this x cubed term and just write x instead. And for the rest time, you just write a small x squared. This means that the terms after x will be strictly smaller than x squared. As near x equals 0, x cubed will be much smaller than x squared. You can see what is the case in the graph of sine x, the red one, and x minus 1 over 3 factorial, which is 6 times x cubed. So this is the blue one. In the vicinity of x equals 0, these two functions are basically the same. They overlap exactly at x equals 0. And the next letter is probably one of the most famous and the most mispronounced Greek letter. In English, it's pi, but in Greek, it's p. So the uppercase is used to represent the product notation. It's useful to shorten expressions and make it seem cooler. So if you've seen this expression, pi of n from n equals to 1 to 5 just means 1 times 2 times 3 times 4 times 5. And you may have seen this in some science movies where some scientists just write a bunch of these product notations, and with the summation notation, the sigma, which I will talk about later on the blackboard, trying to intimidate you. And the upper one maybe some infinity, and it's a very long and complicated expression, but it's actually not that hard. And the lowercase, I believe I don't need to talk about this. The ratio between circumference and diameter of circle, approximately 3.14159. This thing first appeared in circle, but as people study it later, it appears in almost every field. It appears in tricks, it appears in celestial mechanics and quantum mechanics, and everywhere. The next one is rho. The uppercase is the same as P in English, but makes an rho sound in Greek. So it's used for pressure, as in the ideal gas equation. The pressure of a gas times its volume will be proportional to the temperature. And for the smaller rho, it looks like a P, but it's not a P. It is used to represent the distance from the origin to a point in the spherical coordinate system. And talking about spherical coordinate system, I have to mention there are two conventions used by different people. So the first one for physicists is rho, phi, and theta. And the second one for mathematicians is rho, theta, and phi. So physicists use theta to measure the altitude. It's the angle from the z-axis, the first one, this one here. And the mathematicians use theta to measure the argument, which is the angle from the positive x-axis, is this one here. So depending on your context, these two angles may be swapped around. You have to be careful of the text you are reading. The next one is sigma. The uppercase, the square looking one, is used for the summation notation. It just means substitute the value of the I in here and add them all up. It's useful to shorten expressions and makes them seem cooler. The lowercase one is used to represent the standard deviation. It's a complicated looking formula, but you use a calculator to do it for you anyway. And nowadays, if you are an experimental physicist, you need your data to be 5 sigma away from the expected value to claim for discovery. So for example, if you are a particle physicist and you discovered a particle with a ridiculously high energy in your particle accelerator, you need to compare its energy to the predicted energy. If say the predicted energy is 0 and the standard deviation is 1, so 1, 2, 3, 4, 5. If its energy is greater than 5, then you can say you have found a new particle. The next one is tau. The uppercase is the same as T in English. It's used to represent the Cauchy stress vector, or sometimes also called traction by engineers. So it will be equal, according to Cauchy's formula, the generalized dot product of the Cauchy stress tensor with a normal vector to the surface. It tells you the force per unit area that acts on an internal surface of a material. And the lowercase one is like an T but without a head. It's used to represent the proper time. So tau is T divided by gamma. If you remember your gamma from our third slide, the Lorentz factor. This is the shortest time you can measure, and the proper time is defined to be measured at the rest relative to an event. The next one is upsilon. In this form, it may look strange, but in this form, it is exactly the Y English. And it's used to represent the spherical harmonics. As you can see, it's this horrible function, and it's bivariate. The two independent variables are the angles in the spherical coordinates. And M and L are also two parameters, that's the quantum numbers. It is used to describe the shape of the electron cloud in the atom, which is basically what you get when you solve the angular Schrodinger equation for a spherical symmetric system. The lowercase upsilon, this is not a V or a nu, it's just another Greek letter with a round bottom, and it's not used in any scientific context I can think of. And next one is phi. The uppercase is used to represent a flux. It's basically the rate of flow of a quantity through a surface. And from Gauss's law, the flux of the magnetic field through a closed surface S, given by this closed loop on the integration sign, is always 0. So what this tells you is that magnetic field lines always form closed loops. If you have a magnet here, and you draw out its magnetic field lines from North Pole to the South Pole, and you draw any closed surface, a Gaussian surface here, then you have found the number of magnetic field lines. In our case, into the surface is 1, 2, 3, will be equal to number of magnetic field lines out. In this case, also 3. So the net flux will be 0 for all the time. And for this one, directly in the middle, this field line in the magnetic moduling will be straight to the infinity, and the South Pole here will be coming straight from the infinity to the South Pole. And the lowercase phi is used to represent an angle when theta is already being used. So for example, in the polar coordinates, it's rho and theta, and in the spherical coordinates we have talked before is rho, theta, and phi. And the next one is chi, similar to English's x. The uppercase one is used to represent the equation of motion of the big object when the small x has already been used. So in Newton's second law for large mass, F equals ma, and the acceleration can be written as x double dot, which means the second derivative of the position with respect to time. So xt will represent the position of the object at any instance in time. And this is for the object moving in one dimension. And the lowercase x, or chi in this case, is the way I handle my x. Just imagine how many ways there are to write x. So for my personally, I like to add a stroke here and also a stroke here. By this way, I can distinguish my x from the multiplication symbol, especially in vectors where you have a cross product. And the next one is psi. They are used to represent the wave functions of a quantum particle, which is used to describe the distribution in space of probability density function in the smallest scale. So the uppercase one is used in the full Schrödinger equation, written like this. The left-hand side, partial t, this tells you how the wave function evolves in time. And the right-hand side, remember this, the Hamiltonian operator, it tells you how the wave function will respond to the energy distribution in space. The lowercase psi is also the wave function, but it usually represents the time-independent one. So in the time-independent Schrödinger equation is simplified from separation of variables. It tells you that the energy times the wave function is the same as the Hamiltonian operator acting on the wave function. Okay, now for the last letter, the omega. The uppercase one is the unit for electrical resistance, which is ohm, is equal to a volt divided by ampere. And the written out in SI base units is like this, but I don't think you will ever write it in this way. This is straightly from Ohm's law, which states that in unit sense, 1 ohm of resistance means 1 ampere of current is flowing through 1 volt of potential difference. And for the lowercase omega, beware it's not a W, the bottom is round. It's used for the angular frequency, which is 2 pi. So this is the angular part times the normal frequency f. Or in the vector sense, it can also represent the angular velocity. Although one is scalar and one is a vector, they actually have the same units. Both are measured in radians per second. And that's all the Greek letters you need to know. Thank you guys.